Hello, this is AP Calculus Lecture 5.2, where we're going to be integrating natural log functions. If you want, you can turn your book to page 327. We'll be working some problems from that page. So let's start out with what's something that you learned in 5.1, and just remember the derivative of the natural log of the absolute value of x. Remember, it has to be absolute value. Can't take the natural log of a negative. Is equal to 1 over x. So, therefore, if you were to integrate 1 over x dx, then that's going to be the natural log of the absolute value of x. You're just going from 1 over x to the natural log of the absolute value of x. Okay, so we've got some trig formulas for you to memorize. So I'm going to put those over here. So you already know that the antiderivative of cosine x dx is just sine x plus c. And the antiderivative of sine x dx would be minus cosine x plus c. Okay, but we need to learn to integrate the other trig functions. So how about tangent x dx? Well, I'm going to show you how we can get this in just a minute, but for now it's minus the natural log of the absolute value of cosine x plus c. And then the antiderivative of secant x dx is going to be the natural log of secant x plus tangent x. The absolute value of that plus c. And if we get into cotangent x, that's going to be the natural log of the absolute value of sine x plus c. And then cosecant x is minus the natural log of cosecant x plus cotangent x plus c. Now, you know, you're just going to have to memorize tangent x, cotangent x, and I'll show you how we get tangent x in a minute. You know the derivative of secant x is secant tangent, so that kind of helps you memorize that it's the natural log of secant plus tangent, so that might help a little bit. And the derivative of cosecant x is minus cosecant cotangent, right? So the antiderivative of cosecant x has a cosecant and a cotangent in it. You just have to add there. And there's also that minus out front. So let me show you how we get this one. You could do the same for the other three. But let me show you how we integrate tangent x. So let's rewrite this as sine x over cosine x dx. If we let u be cosine x, then du is minus sine x. So I picked cosine x because we can't deal with du on the bottom. So minus sine x dx. That's almost what we need. Let's put a minus out front. Minus du is sine x dx. All right, so we can rewrite this in terms of u. That minus comes out front, and I would have du over u. Now, du over u is the same as 1 over u du, okay? It's the same. So if you see that du over u, you know that this would be, the antiderivative of that in terms of u would be minus the natural log of the absolute value of u plus c. So that would be, if you put u in the problem, you got to take u back out. So minus the natural log of the absolute value of cosine x plus c. So that's how we get right here. And you could do that same exercise for all of them. You could rewrite that as 1 over cosine, cosine over sine. You could rewrite this right as 1 over sine and go through the process, and you would come up with this. But I'm not going to do that for all of them. I'm just going to encourage you to memorize these antiderivatives. And let's see if we can work some example problems here. So let's try number 2. On page 327. I'll erase all this if I can't work it here, but we have 1 over x minus 5 dx. Now, usually with these, what you're seeing, unless it's trig, usually what you're seeing is you're going to let u be the denominator, okay? Because we're trying to get to a version of this here. Okay, so if we let u be x minus 5, du is just going to be 1 dx or dx. And that's all we have on the top here. So we can rewrite this integral in terms of u as 1 over u du, or du over u, same thing. Well, that's going to be the natural log of the absolute value of u plus c. And now we can substitute back in for that u. So the natural log of the absolute value of x minus 5 plus c. Now let's check this by taking the derivative like we did in chapter 4 and see if we end up back here. So the derivative of the natural log of x minus 5 is going to be 1 over x minus 5 times the derivative of the inner function, which is just 1. And there you go. You're right back here. So it does indeed check. Now I won't check all of them. I'll probably check one more as I do these examples. But on a test, you should check every single one of them. All right, let's try number 6. So what we have with number 6 is x squared over 3 minus x cubed dx. So you want to pick a u that when you take the derivative of it, the derivative is sitting in the problem. It might be off by a constant, right? So if we let u be 3 minus x cubed, then du is minus 3x squared dx. Well, I need it to just be x squared dx. So if we multiply both sides by negative 1/3, that's going to be x squared dx. So that's minus 1/3. And then we would have du on top, x squared dx is on top, over 3 minus x cubed, that's u. And so that's minus 1/3 times the natural log of the absolute value of u plus c. Now we can substitute back in our u, and that would be 3 minus x cubed plus c. And if you check that, that will, by taking the derivative, the derivative will equal this right here. So I'll let you check it if you want to, or you can just trust me. All right, let's do another one. Okay, we're going to do example 10. All right, that is, we're going to integrate x plus 3 over x squared plus 6x plus 7. Okay, so let's let u be the denominator, x squared plus 6x plus 7. Du would be 2x plus 6 dx. We need it to be x plus 3 dx, so if I multiply both sides by 1/2, I would have x plus 3 dx. So that's exactly what we need to be on top. X plus 3 times dx is now du, and the bottom is u. So we know that that is 1/2 times the natural log of the absolute value of u plus c. That's the antiderivative of du over u, or dx over x, right? So that's 1/2 times the natural log of the absolute value of x squared plus 6x plus 7 plus c. Now let's check this one. I'm going to take the derivative of that. So it's going to be 1/2 times 1 over x squared plus 6x plus 7 times 2x plus 6. All right, so this 2 and this 2 will cancel, and that 2 and 6 there becomes a 3, so you end up having x plus 3 over x squared plus 6x plus 7. And that's exactly what you have here. That's what you need. All right. Let's try number 12. Okay, here we have 1 over x times the natural log of x squared dx. Now, just like when taking derivatives, we want to use the properties of logs whenever we can. So I'm going to use the properties of logs to rewrite this as 1 over. I'm going to bring that 2 out front. So it would be 2x natural log of x dx. Now I can bring that 1/2 in front of the integral, 1 over 2. And it's just 1 over x natural log of x dx. So I can kind of see if I let u be the natural log of x, then du is 1 over x dx. And that's sitting in the problem, 1 over x times dx. So I could rewrite this as 1/2 out front, and then it would just be du over u. If you don't see that, just take a moment and stare at it. But du is 1 over x dx, so the du goes on top. And then u is on the bottom. That's just natural log of x. All right, so that's going to be 1/2 times the natural log of the absolute value of u plus c. So it'd be 1/2 times the natural log of the absolute value of the natural log of x plus c. All right, well, that's pretty cool. So you've got a natural log within a natural log there. All right. And you could check that if you want. Go ahead and check that and see if you end up back there. All right, but you will. All right, we are moving right along. Just 2 more examples. So example 20. So we're going to get into these formulas. That's why I didn't really want to erase them. Let's say we're taking the antiderivative of tangent 5 theta d theta. All right, so if it were just tangent theta, we could go straight into this formula, but it's 5 theta, so this is a u substitution. So if we let u be 5 theta, du is just going to be 5 d theta. We need it to just be d theta. So 1/5 du is d theta. And we can rewrite it as 1/5 tangent u, right? U is 5 theta, so tangent u du. Okay, now we can go to this formula, so that's going to be minus 1/5 the natural log of the absolute value of the cosine of u, right? We're just following this, plus c. So that's minus 1/5 times the natural log of the absolute value of the cosine of 5 theta. Don't leave it in terms of u, plus c. Now let's check that by taking the derivative. Okay, so it's going to be minus 1/5 times 1 over cosine 5 theta times the derivative of cosine 5 theta, which would be minus 5 sine 5 theta. So the negative 5 and the negative 1/5 will cancel, and you would end up with sine 5 theta over cosine 5 theta. That's tangent 5 theta. And there you go. You're back to the beginning. So definitely strongly encourage you, especially on a test, to check. And you should check some of your homework just so you get used to checking. Some of it you can some of them are simple enough you can check with just your eyeballs and do the derivative in your head. But if it's something a little more complex, you should check it on paper. All right, our last example is example 22. We're going to integrate secant x over 2 dx. So if we let u be x over 2, then du is 1/2 dx. We need it to just be dx, not 1/2. There's no 1/2 in here, right? So if we multiply both sides by 2, 2 du is equal to dx. And I can put a 2 out in front of the integral. I have secant u du. So let's look at the formula. That's going to be a natural log of secant x plus tangent x, or secant u. So that would be 2 times the natural log of the absolute value of secant u plus tangent u plus c. We're almost done. The absolute value of secant x over 2 plus tangent x over 2 plus c. All right. Well, there you go. That does it for the examples. Now let's talk about the homework. So your homework is on page 327. You're going to do 1 through 13 odd, 19 through 25 odd, and number 63. So for number 63, you need to remember the average value formula. All right, we did this in chapter 4, and it's 1 over b minus a. You're going to integrate from a to b of f of x dx. So everything's the same except you multiply your answer by this coefficient. All right, let's take a look at these homework problems and see if there's anything you need some instruction with. So 1 through 13 odd. These are just like the examples we did. 19 through 25 odd, you're going to be using the trigonometric formulas, so no problem on that. And then 63 is a word problem that we talked about. You got to find the average price there on number 63. So just use that. Integrate this function from 40 to 50, and you'll use that formula. So, all right, that does it for this lecture. And I will talk to you on the next one.